Have you ever wondered how an AI can just look at a picture and instantly know what's in it? Well, that little bit of magic is called computer vision. And today we're going to dive into how it all started by looking at a revolutionary model from way back in 1998 that basically taught computers how to see. It's called LeNet 5. So, here's our game plan. First, we're going to tackle what I call the pixel problem. Why this is so tough for computers in the first place. Then we'll get into the big idea behind convolutional neural networks, or CNNs, and their three main building blocks. After that, we'll actually assemble the classic LeNet 5 model. And finally, we'll look at the absolutely stunning results that really did change everything. Okay, so let's start with the big challenge, right? It's called the pixel problem. And it's the main reason that for decades, computers were just completely blind. I mean, think about it for a second. A little kid can look at a messy, handwritten 2 and know what it is in a heartbeat. But for the longest time, that super simple task was pretty much impossible for even a powerful computer. So, what was the disconnect? Well, the whole problem was the approach. A traditional neural network would take an image and just flatten it, turning it into one long, jumbled up list of pixels. It completely destroyed the structure. It had no idea that a pixel being next to another pixel is what creates a line or a curve. For a human and for a CNN, that spatial relationship isn't just important, it's everything. So, how in the world do you teach a computer to see that structure? The answer was this totally revolutionary shift in thinking, and that is the big idea behind the CNN. The breakthrough was actually kind of simple, but really profound. Just stop trying to look at the whole image all at once. Instead, a CNN acts like a detective. It scans the image with a tiny sliding window, a little magnifying glass, if you will. And it's not looking for a 2. No, it's looking for much simpler local patterns. A little vertical edge here, a sharp corner there. It learns to see by starting with the most basic parts of any picture. Now, this whole scanning approach, it relies on a really elegant and powerful set of tools. So let's break down the 3 key building blocks that make all of this work. First up, we've got convolution, or conv2D. This is our pattern detector. I want you to imagine you have a whole bunch of these tiny 5 by 5 pixel magnifying glasses, and each one is trained to find just one specific thing, like a perfect horizontal edge, or a diagonal line, or a slight curve. As these little filters slide across the image, they light up, creating these things called feature maps that show exactly where they found their pattern. Next in the toolkit is pooling. This is our shrinking tool. See, once we have all those maps of where the patterns are, we don't really need every single little detail. It's kind of noisy. So pooling brilliantly simplifies things by taking a small 2 by 2 area and shrinking it down to just 1 pixel, keeping only the strongest signal. It's how the network learns to just focus on what really matters. And finally, there's a more modern tool that's absolutely crucial today: batch normalization, our training accelerator. Now, this wasn't in the original LeNet 5, but it's a game changer. It basically stabilizes all the data that's flowing through the network, which dramatically speeds up how fast it can learn. We're talking sometimes up to 10 times faster. So, quick recap of our toolkit. Com2D is the pattern detector. It finds all the local features. Pooling is the shrinking tool. It cuts down on the complexity. And batch norm is our training accelerator, making the whole learning process way faster. With these tools in hand, we're ready to build a legend. All right, now let's see how these blocks were first put together to create a true classic, the LeNet 5 model, all the way back from 1998. This is the architecture that really kicked off the entire deep learning revolution in computer vision. So here's the journey an image takes inside LeNet 5. It starts with a convolution layer that just finds the most basic edges. Then a pooling layer comes in and shrinks everything down, keeping only the strongest signals of those edges. The next convolution layer is even more powerful. It uses those simple edges to find more complex shapes, like corners and curves. After one last shrink, this super refined information, the pure essence of the shape, gets passed to the final layers, which make the call.
Yep, that's a 2.
So that's the blueprint. But the big question, of course, is how well did it actually work? Well, this is where we get to the really stunning results. On the standard test for handwritten digits, LeNet 5 achieved 99.2% accuracy. I mean, for its time, this was absolutely groundbreaking. It was near perfect performance on a task that had totally stumped computers for years. But here's the kicker. It wasn't just about the accuracy. It was the incredible efficiency. LeNet 5 got this result using 50 times fewer parameters. Those are the little internal knobs the network tunes than a traditional network would have needed for the same job. And let's put that in real numbers for a second. LeNet 5 used just over 62,000 parameters. A comparable traditional network, it would have needed over 1 million. That's the power of looking for patterns instead of trying to brute force memorize every single pixel. So we know it works, and we know it's incredibly efficient. But what is it actually learning? What does a CNN see inside its virtual brain? This is honestly the most beautiful part of the whole thing. It learns in layers, just like we do. The very first layers, they learn to see the simplest things you could imagine: basic edges, lines, and gradients. Then, the next layers take those simple edge maps as their input, and they learn to combine them into more complex shapes, things like corners, curves, and circles. Finally, the last layers assemble those complex shapes to recognize whole objects, like the complete form of a 7 or a 4. It's like it's building a visual vocabulary, from letters to words to full sentences. And here it is, the ultimate proof that it's truly learning to see and not just memorizing. When they took this exact same model, trained only on handwritten numbers, and tested it on a totally different, harder data set of clothes, like t-shirts, shoes, bags, it still got almost 90% accuracy. This proves that the features it learned, like edges and curves, are universal. They actually generalize to new problems. And that, my friends, is the hallmark of true intelligence. So this leaves us with a really fascinating final thought. LeNet 5 had just a handful of layers. Today's models, things like ResNet, can have over 100. So if this simple design from 1998 could learn such a robust visual language, what kind of complex, abstract concepts do today's massive AI models truly see